Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Dear students, today we will discuss our lecture number 2. Course title is Advanced Physical Chemistry and the course is Conductometry. Course code is CHEM3117. My name is Dr. Rana Farat Mahmood. Let us start our topic. First of all, we will discuss our contents. Number 1 is effect of dilution on conductivity. Here we will discuss that on diluting the electrolytes, what is the effect of dilution in electrolytes on their conductivities, means specific conductivity, molar conductivity and equivalent conductivity. The second topic will be discussed is Coleridge's law. This law, why this law is stated, what is its statement, and then how it is related to the conductivity. Then the third is applications of Coleridge's law, that Coleridge's law की applications क्या होंगी and how it will act on conductivity. The fourth topic will be about calculations of molar conductivity at zero concentration, means lambda 0 m, by Coleridge's law, that how Coleridge's law is used to calculate molar conductivities at zero concentrations, and what is molar conductivity at zero concentration. All the things will be discussed. Okay, let us start our topics at slide number 4. Dear students, at slide number 4 we will discuss about effect of dilution on conductivity. The first point is that on dilution of electrolytes, means their concentration decreasing, on the decreasing their concentrations, the specific conductivity will be decreased. Okay, let me explain an example. If we take 1 ml, then we say that it contains 4 ions. If we take 2 ml, then it contains 8 ions. Okay, when we dilute it, means when we add 2 ml in the 2 ml electrolyte, we dilute 2 ml with 2 ml water, it comes 4 ml. But as I mentioned earlier that 2 ml of electrolyte contains 8 ions. For example, if I add 2 ml water in the 2 ml electrolyte, then it contains the same amount of 8 ions. So we have the ratio 4 into 8. 4 8 means 4 ml total volume, and total volume contains 8 ions. So dividing 4 on both sides, we see that 1 ml contains only 2 ions. So the number of ions per unit volume decreased because they are on their dilution, their specific conductivity decrease. In this way, specific conductivity is decreased on their dilution. You should know that specific conductivity is different from molar conductivity and molar conductivity is different from equivalent conductivity. Specific conductivity, as we mentioned in lecture number 1, that specific conductivity is the conductivity of an electrolyte whose volume is specified. And molar conductivity is the conductivity of an electrolyte whose molarity will be given us. And equivalent conductivity is the conductivity of the electrolyte whose normality will be calculated. So coming to our second point, that is equivalent and molar conductance both increase. At this point we have two reasons. The first reason is that when we dilute an electrolyte, then one thing that happens is that the hindrance decreases. The hindrance between electrolyte molecules decreases. When the hindrance decreases, then the movement per unit time increases. It means it comes to our second reason. First reason was that the hindrance decreased. The second reason is that the ionic mobility will be increased because the hindrance decreased, so ionic mobility will be increased. Ionic mobility means movement of ions per unit time will be increased. When the movement per unit time will be increased, then per molar their conductivity will be increased. The third point is that conductance of all electrolytes increases with temperature. Here the overall point is mentioned that conductance, not specific, not molar, not equivalent. The conductance of all electrolytes increases with the temperature. So let me explain these second point in the graph. You see in the graph below that electrolytes, we have two types of electrolytes. One is strong electrolyte and the other is weak electrolyte. The strong electrolyte is the KCl and the weak electrolyte is the acetic acid CH3COOH. In case of KCl, when we go from right to left in the x-axis where we have given concentration per mole per liter, mole per liter. When on the x-axis we go from right to left, it comes that the concentration of KCl decreases but the dilution increases. As we know that when we dilute any substance with the water, then its concentration decreases but dilution increases. Okay, when dilution increases, then on the y-axis the molar conductance increases. In case of weak electrolyte, we see that on x-axis when we decrease its concentration by diluting it with water, then its molar conductance suddenly increases. At start its molar conductance is very low, then at very high dilution its molar conductance suddenly increases much. But here is one notable thing is that KCl curve means KCl line, graph line touches on y-axis on a maximum value, but The acetic acid graph line does not touch on the y-axis. It means that for a strong electrolyte, we have come a point where molar conductance is maximum. This point on which KCl graph line touches on y-axis, this point is called maximum dilution. It is also called zero conductance. It is also called limiting molar conductance, or it is also called molar conductance at zero conductivity, or molar conductance at zero concentration. Okay, when we go to the weak electrolytes, acetic acid, then we have come to know that its graph line does not touch on y-axis, so we don't have a point where we can calculate its molar conductance at zero concentration. For the calculating molar conductivity of weak electrolytes at their zero concentration, at their maximum dilution, we have made we have studied a law that is Collin's law, and it will be explained on the next slide, number 5. Students, we are discussing about conductometry, and here we have discussed earlier that strong electrolytes have a molar conductance at zero concentration, but the weak electrolytes does not have their value on their zero concentration, does not have their molar conductivity value on their zero concentration. So for calculating their molar conductivity at their zero concentration, or for calculating their limiting molar conductivity, we have a law called Collin's law. Its statement is that limiting molar conductivity of an electrolyte means of a weak electrolyte. Here we should mention that weak electrolyte, because for a strong electrolyte we have calculated their molar conductivity by graph method, but graph method does not give us a calculation about the weak electrolytes limiting molar conductance. So by Collin's law we can calculate their limiting molar conductance. Okay, we are coming to our statement of Collin's law. Limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cations of that electrolyte. Mathematically, lambda infinity means that electrolyte. For example, we say that we have acetic acid, then lambda CaCOH will be equal to lambda A. Lambda A means the limiting molar conductivity of anions, and plus lambda C means limiting molar conductivity of cations, means positive ions. Their sum is equal to the limiting molar conductivity of electrolyte, where lambda A and lambda C are known as ionic conductance of anion and cation at infinite dilution respectively. On slide number 6 we will discuss about its applications, and it will be noted that how Collin's law is applied to the weak electrolyte, and in what way it is useful. So Collin's law can be applied on the number 1 point is that determination for weak electrolytes. It is said that the molar conductivity of a weak electrolyte at infinite dilution, means at their zero concentration, cannot be determined by extrapolation method. Now, here is a question. What is extrapolation method? At our slide number 4 or something, I think it is slide number 4, on which we have discussed about the graph. That graph is extrapolation method. Extrapolation method is the method of calculating limiting molar conductivity of a weak electrolyte by graph. So the graphical method or extrapolation method does not give us the value of limiting molar conductivity. However, values for weak electrolytes can be determined by using the Cordes equation. Number two application is that it is used for the determination of the degree of ionization of a weak electrolyte. Here one thing is notable that weak electrolyte is ionized, and it is ionized on the dilution. Its principle of ionization is given by the Ostwald law. Ostwald dilution law is the law that states that on the dilution of a weak electrolyte it is ionized much. Okay, how much it is ionized? It can be determined by Cordes law. So the number two application is that determination of the degree of ionization of a weak electrolyte. The Cordes law can be used for determining the degree of ionization of a weak electrolyte at any concentration if it is the molar conductivity of a weak electrolyte at any concentration C and is the molar conductivity of a electrolyte at infinite dilution, then the degree of ionization is given by molar conductance at given concentration by or over molar conductance at zero concentration. It means that the second application is that we can determine a degree of ionization of a weak electrolyte by making a ratio between the molar conductance of that weak electrolyte at given concentration to the ratio of molar conductance at given concentration to the molar conductance of that weak electrolyte at their zero concentration or at the infinite dilution. So basically number two application is a ratio, not more than anything. Okay, this was the applications of Cordes law. Then on the next slide number 7 we will discuss about how we can calculate a molar conductance of any substance that is working as an electrolyte. Dear students, it is our slide number 7 about Cordes law, that how to calculate lambda naught m. It is symbol for molar conductance at zero concentration by Cordes law. One thing you should note that limiting molar conductance for any electrolyte is the summation of individual contributions of cations and anion of that electrolyte. So we are discussing an example of HCl. Here one thing is also notable that any electrolyte we are calculating for its molar, for its limiting molar conductance, then we will add two other strong electrolytes, and then we will add them, and then we will subtract from them common ions, we will subtract from them. Okay, first equation is that when we take HCl as an electrolyte, it is dissociated into its respective cations and anions, which are hydrogen ion and chloride ion. So limiting molar conductance of HCl at zero concentration will be equal to limiting molar concentration of hydrogen ions at their zero concentration plus limiting molar conductance of chloride ions at their zero concentration. Similarly, in equation number 2, we have ammonium chloride, because I have said that besides the HCl, we will add two other strong electrolytes. One is ammonium chloride, the second is water. So, in case of ammonium chloride, its limiting molar conductance will be equal to molar conductance of ammonium ions at their zero concentration plus molar conductance of chloride ions at their zero concentration. In the equation number 3, we have H2O water, limiting molar conductance of water at their zero concentration will be equal to limiting molar conductance of hydrogen ions at their zero concentration plus limiting molar conductance of hydroxyl ions at their zero concentration. These three equations we have written, and then we have calculated their molar conductivities of ammonium hydroxide. So you will be given a question that calculate limiting molar conductance of ammonium hydroxide. Then you will be given equations, then you have to calculate them by this method, that subtracting equation number 1 from equation number 2 and then add equation number 3. So left side will be subtracted of equation number 1 from equation number 2, then left side of equation number 3 will be added. So in the below we have lambda naught ammonium chloride minus lambda naught HCl plus lambda naught H2O will be equal to lambda naught ammonium ions plus lambda naught chloride ions. This is our equation number 2. Then we are subtracting minus lambda naught chloride ions of equation number 1. It is the right side. Then we are subtracting from this lambda naught hydrogen ions. Then we are adding equation number 3 right side, that plus lambda naught hydrogen ions plus lambda naught hydroxyl ions. Then common ions and their opposite signs will be cancelled out, that such that lambda naught chloride will be cancelled from lambda naught chloride, and lambda naught hydrogen ion will be cancelled from lambda naught hydrogen ions. Then in the below we have lambda naught ammonium chloride minus lambda naught HCl plus lambda naught water will be equal to lambda naught ammonium ions plus lambda naught hydroxyl ions. Means we have calculated that lambda naught ammonium hydroxide, which is a weak base, its molar conductance at zero concentration is calculated by subtracting the molar conductance of ammonium chloride at zero concentration minus molar conductance of HCl at 0 concentration, and then we will add the molar conductance of water at 0 concentration. So here we have calculated the molar conductance of ammonium hydroxide at 0 concentration, which is a weak base. Okay, in this way, if we have given questions that calculate ammonium hydroxide molar concentration from the equations, then in this way you can calculate their limiting molar conductance. Dear students, it is our end of lecture number 2 for conductometry. Any question related to the lecture you can ask. Thank you very much. Allah Hafiz.